Hi everyone. This video is for section 1.4 in the Honors Algebra 2 textbook. It is called Graphing Sequences. So if you think about it, sequences, first term is 2, second term is 3, third term is 4. What we're really going to be doing is plotting points today. You can think of it as being that simple because it really is. The first two slides of today's lesson, I'm going to do a little more kind of reviewing of the whole chapter to just kind of bring everything together. And then the third slide, we will practice graphing sequences, and that will be it for the day. Should be a fairly straightforward video. Fingers crossed. All right, looking here, I've got a series of statements. You don't have to write them all down, but you might want to sketch some of them down that don't feel quite as obvious to you. Some will feel obvious and you wouldn't really have to. But let's just read through them, and I'm hoping as you're listening to this in your mind, you're going, oh yeah, sure, okay, yep, that makes sense. Just kind of a little checklist. So the first statement, maybe it seems obvious, maybe it doesn't, but that arithmetic sequence have linear graphs. Because if you are arithmetic and you're growing by 2 each time, your graph, when you plot those points, will look pretty linear. Where a geometric sequence would have a curved graph, because if you start here and you multiply by 2 each time, it's going to double, and when you plot your points, it will look more graphed, not so straight. That should be over a little bit more. All right, the next statement, it says when the common difference of an arithmetic sequence is positive, the linear shape slopes upward from left to right. Seems fairly obvious. If we are adding 5 each time, it will slope upward. Where if the common difference of an arithmetic sequence is negative, the linear shape will slope downward from left to right. So if we're subtracting 5 each time, those points, you can kind of imagine a straight line going down. All right, seems fairly straightforward. The next one, when the common ratio of a geometric sequence is greater than 1, the curve shape increases. So remember, if that ratio is greater than 1, we're having geometric growth. So it would make sense that the curve will go up. Where if the common ratio is between 0 and 1, the curve shape will decrease from left to right. So that curve shape will head down. You could kind of imagine if you connected these, it would go like that. All right, then lastly, the thing about a shifted geometric is it levels off to a non-zero value. So if we're talking about the cocoa cooling, it doesn't level off down on the x-axis, it leveled off at room temperature. So it leveled off at that non-zero value right about there. And if we're having like a shifted geometric growth, it would look more where it's growing and then would eventually level off, in this case right here. So since this section is called graphing sequences, these are good kind of generalizations to think about. If the points you make are linear, if they're more shifted on a curve, if they go up, if they go down, in which way they will level off. There are all kind of things to think about. All right. Going back here, describe each sequence. So using our vocabulary again, just trying to get more and more comfortable with it. Describe each sequence using exactly 3 of these terms: arithmetic, geometric, shifted geometric, increasing, decreasing, linear, nonlinear. I'm going to give you a huge clue picking 3 terms. The first term would come from this first grouping. You'll either have a sequence that's arithmetic, geometric, or shifted, and then the second grouping, or the second term, it'll either be increasing or decreasing, and then your third grouping, your third term, it'll either be linear or nonlinear. And hopefully you'll see some patterns. Arithmetic will be linear, geometric will be nonlinear, and shifted geometric will be nonlinear. So there's little shortcuts and pairings that hopefully you'll start to connect. So look at this first one. U sub 0 equals 200. U sub n is the previous term plus 4. U sub n minus 1 plus 4. But hopefully that plus 4, you recognize it as the common difference. So it's really easy to see that it's arithmetic. And since the common difference, since we're adding 4 each time, you're going to know it's increasing. And just like on the last slide, we talked about how arithmetic sequences will always be linear. So those would be 3 terms that would make sense to describe this guy. All right? Look at this red one down below. U sub 0 equals 15. U sub n equals 2 times the previous term. 2 times u sub n minus 1. Well, I hope that this is a big clue to you that multiplication, that there's a common ratio. So we're living in geometric. Hopefully you can see, I didn't spell increasing right there, did I? That it's increasing. What would it have to be? What would the ratio have to be for it to be decreasing? Will it be less than 1? So if you got a ratio right here, if it was 1/2, 1/5, 0.2, 0.7, then it would decrease. So the decreasing is when that ratio is between 0 and 1. And then hopefully you're comfortable with the idea that geometric, when you graph them, it will look, those dots will make a nonlinear pattern. All right? This last one, it's recursive. U sub 0 equals 200, but now the rule is you take the previous term times 0.2 and you add 4. So that's a classic shifted geometric. I hope you recognize that now. That shifted geometrics, it has that geometric portion with something added or subtracted on the end. But now the question is, and so that'll make it nonlinear. But the question is it increasing or decreasing? It's sometimes hard to know. We're adding 4. So the arithmetic part makes you think it's increasing, but the geometric part, you're only multiplying by 0.2. Remember when that ratio is between 0 and 1, that means decreasing. So which one is it? Well, I think what I'm going to do is just calculate the long run value. And if in the long run I'm higher than 200, it's increasing. If I'm less than 200, I'm decreasing. So then I end up with a 5 for my long run value. So it's clear to see that if that first term is 200 and then the long run it goes down to 5, we're going to have a decreasing sequence. The other option you would have that this would work totally well is just plug in that first one, find u sub 1. So you do 0.2 times 200 plus 4. Let's see what we got. 0.2 times 200 plus 4, we're just at 44. So that would tell you that that first term is 200, the second term is already way down to 44. So that would be a way to see that it's decreasing as well. So it'd be up to you if you'd want to find the second term or the long run value to decide if a shifted geometric is increasing or decreasing. All right. The last slide of the day, you'll want to take some notes here. When we graph sequences, we must keep our graph discrete, not continuous. So a discrete graph, not a continuous one, when you're graphing sequences. And I'll explain what that means in a minute. All right, make it more clear. We have a nice recursive formula here. U sub 0 equals 2, and U sub n is the previous term plus 6. So to me, that's really super clear that it is arithmetic. That common difference is 6. So let's just make a little chart. According to this, the 0th term, the value is 2. It wants 5 ordered pairs. So that will give us 5. So let's plug in now. If I plug in a 1 here, I get a 7. And now I plug in a 7. Let me make this a little bit more clear. So I'm going to have Well, let me back up. That first term is 2. So now I plug the 2 in. 2 plus 6 equals 8. Now I plug the 8 in. 8 plus 6 is going to be 14. Plug the 14 in. 14 plus 6 is 20. Plug the 20 in. 20 plus 6 is 26. So if I was going to make a table of values, it looks like my term number n and the value of the term number, well, when I was on the 0th term, the value was 2. The first term, the value was 8. The second term, the value was 14. The third term, the value was 20. And the fourth term, the value was 26. So those can be made into ordered pairs. It says write 5 ordered pairs, 0, 2, 1, 8, 2, 14, 3, 20, and 4, 26. So there are the 5 ordered pairs that represent the points of a graph in a sequence. Let's actually take a second and graph them so we can talk about discrete versus continuous. So the idea is if we had a graph in quadrant 1, the term number is your n and the value of the term number u sub n. So I look at these ordered pairs and see them as n comma u sub n. You could certainly think of them as x comma y. You're much more used to that. So it looks like on the x-axis where the term numbers are, it goes from 0, 1, 2, 3, and 4. And then on the y-axis where the u sub n, or the value of the term is, it goes from 2 up to 26. So 6, 8, 12. There I counted up by 2's. So if we plotted these, our first point, 0, 2, would be right here. And then 2, 4, 6, 8, 1, 8 would be here. 2, 14 right about here. 3, 20 right about here. And then 4, 26 right about here. So if you are asked to graph a sequence, you do not connect the points, okay? Because you are not finding out what happens between steps. That might be worth writing down. Do not connect points when graphing a sequence. It's a subtle distinction, but it really shows you know what you're doing, because you're not finding out what happens between the steps. That is what it means to be a discrete. So this officially right here is a discrete arithmetic recursive sequence. So you could tell your family that you worked on discrete arithmetic recursive sequences today, and that sounds super, super fancy. When you know, you don't have to tell them the secret. It really is quite simple. Just a graph where you're plotting points, where you're taking the n and u sub n and changing them into ordered pairs so you can graph. All right, nice work today. That's it for your videos.